All right, today we're diving into how data science is completely changing the game for industrial maintenance. We're talking about moving beyond those old, rigid schedules, and definitely beyond waiting for things to break. We're heading into a future where we can predict failures before they even happen. And how do we do it? Well, we learn to speak the language of the machines themselves, and that language is data.
So to really get why this is so important, let's start with a big, critical business question. Think about a modern factory, a busy production line. What's the actual financial hit when a key piece of equipment just suddenly stops working for just 1 hour?
The number is just staggering. For a typical factory, you're easily looking at over €250,000. I mean, that's lost production, staff standing around, potential penalties for late orders, and, of course, the emergency repair costs. That one number really tells you everything you need to know about how high the stakes are here.
Now, if we're going to tackle this with an engineering mindset, we have to be precise with our words. A fault is not the same thing as a failure. A fault is when one little component starts to go off spec. Maybe a bearing starts vibrating just a tiny bit more than it should. A failure is when the whole system just stops doing its job. So our entire goal with predictive maintenance is to catch those little faults, to prevent the big failures.
So here's our game plan. First, we're going to dig into the true cost of failure to understand the problem. Then we'll talk about how we can literally listen to the machines by looking at their data. From there, we'll see how our methods have gotten smarter, going from simple rules to slick machine learning. After that, we'll see how these models actually get used in the real world. And finally, we'll wrap it all up with the most important part, the engineering decision that makes it all worthwhile.
Okay, so let's start by putting some numbers on this challenge. In engineering, if you can't measure it, you can't manage it. So how do we actually talk about reliability in concrete terms? And how do we start to classify all the different ways that equipment can break down? Well, to measure performance, we use a few key metrics. First, there's mean time between failures, or MTBF. That tells you how reliable a piece of gear is. Then there's mean time to repair, or MTTR, which tells you how fast you can get it back online. And those two feed into the big one, overall equipment effectiveness, which is kind of the master's scorecard for productivity. At the same time, we have to know what kind of problem we're dealing with. Is it slow, gradual wear and tear? Was it a sudden, catastrophic snap? Or is it one of those super frustrating on-again, off-again intermittent faults? Each one needs a totally different predictive strategy. To predict any of these failures, we need to listen. And in our world, listening means collecting data. So what are the actual vital signs we're monitoring on our industrial equipment? Turns out we can tap into this incredibly rich stream of information. Vibration sensors can literally feel an imbalance. Thermocouples are watching for any signs of overheating. We can even monitor the electrical current to see if a motor is straining. And on top of all that, we have logs, alarm codes, event logs, even notes from the operators themselves. All of this raw data, that's the fuel for our entire predictive engine. So take a look at this. This is real data. At first glance, it just looks like a messy cloud of dots, right? Each dot is a measurement of RPM and vibration from a generator. But here's the thing. Hidden inside this noise is a pattern. And our job as data scientists is to build a model that can find the signal in that noise, the signal that separates healthy operation from an impending failure. And this is what that data actually looks like under the hood. It's a classic time series format. For every single timestamp, you've got a machine ID, the sensor that took the reading, and the value it recorded. This clean, simple, structured format is the absolute foundation for everything we're about to build. Okay, so we have all this data flowing in. What's the very first, most basic thing we can do with it? Well, we start with simple rules, but as you're about to see, we pretty quickly realize we need to evolve to something a whole lot smarter. And this slide just perfectly captures that leap in thinking. On the left, you have a fixed rule. If the temperature goes above 100 degrees, send an alert. It's simple, but it's brittle. I mean, what if the machine is supposed to run hotter when it's under a heavy load? The statistical approach on the right is so much more intelligent. It doesn't ask, is the temperature high? It asks, is the temperature abnormally high compared to how it usually behaves? That simple shift in perspective is a total game changer. And that idea opens up this whole world of anomaly detection. We've got tools for this. We can use something simple like a z-score to spot a weird reading from a single sensor. Or we can use more powerful algorithms like an isolation forest, which is amazing at finding really complex anomalies across many sensors at once. We can even build a model to forecast what a sensor reading should be in the next minute.
and then trigger an alert if the real value is way off from our prediction. But what if we don't just want to find random, weird events? What if we want to predict a very specific type of failure that we've seen before? Well, for that, we bring out the big guns, supervised machine learning. So this is a really crucial shift in what we're trying to do. We are no longer just looking for things that are odd. Now, we're taking all our historical data, where we know exactly when and how a machine failed in the past, and we're using it to train a model. A model that can learn to recognize the very subtle multi-sensor fingerprint of that specific failure before it happens again. And this image makes that concept super clear. Imagine all the little crosses are data points from when a machine was running just fine. The triangles are the data points from the hours leading up to a known failure. The whole goal of our machine learning model is to learn that perfect line, the decision boundary, that cleanly separates the two. Once it finds that line, it can look at any new piece of data and classify it as either healthy or at risk. To build a model like that, we follow a really systematic process. It's a standard pipeline. We collect the data, we clean it up, then we engineer new, meaningful features from it. Then we train a powerful model. Something like a random forest or a gradient boosting machine is perfect for this kind of data. After we validate its performance, we finally get to deploy it into the real world, where we have to keep a close eye on it. You know, out of all those steps, I'd say feature engineering is often the most important. We don't just throw raw sensor values at the model. No way. We create new, much more powerful signals. For example, we don't just care about the temperature now. We care if it's trending upwards and how fast. What's the average vibration been over the last 10 minutes? By transforming the raw data into these more insightful features, we make the model's job way, way easier. So, a trained model that's just sitting on a data scientist's laptop, it's pretty much useless. The real value, the real magic, happens when we integrate it into the production environment so it can drive actual decisions on the factory floor. Let's see how that works. And this is where we start getting into some really advanced territory. We can build models that go beyond just saying failure is likely. We can predict the remaining useful life, or RUL, telling us we have, say, 72 hours until a failure. We then serve up these predictions through APIs to maintenance dashboards, or we can even run the models directly on tiny computers right next to the machine. That's edge computing for instant alerts. And of course, we have to monitor everything constantly to make sure the model stays accurate. Okay, this brings us to the final and honestly probably the most important piece of this whole puzzle. A model's prediction is just a number, a probability. The hard part is using that number to make a smart, cost-effective engineering decision.
And really, it all boils down to this one fundamental trade-off. What's worse? Sending a maintenance crew to check on a machine that's actually perfectly fine because of a false alarm, or completely missing a real problem that's about to shut down your entire production line.
This cost matrix lays it out perfectly. A false positive predicting a failure that doesn't happen costs us an unnecessary inspection. It's annoying, but manageable. But a false negative predicting everything's okay when it's not, that is a potential disaster. So what we do is we tune our model's sensitivity based on this business reality. We might actually choose to accept a few more false alarms if it means we can get the chance of a catastrophic miss down to virtually zero. This is how you connect the model's stats directly to financial risk. And that brings us to this final thought, which I think just perfectly sums up the entire philosophy here. It's not just about predicting failures. It's about designing intelligent systems that can identify and manage faults gracefully, creating a future that is more resilient, more efficient, and more reliable. The real goal isn't just to react faster. It's to design a system where those catastrophic failures become a thing of the past.